Hello everyone, this is Chenhui from Cornell University. So today I'm going to present GraphZoom, which is a multi-level spectral approach for accurate and scalable graph embedding. And this is a joint work with Zhixiang Zhao, Yongyu Wang, Dr. Zhang, and Dr. Feng. Graphs are ubiquitous. You can find different graphs from different domains. For example, we have social network where each node is a user and two nodes are connected if they're friends. And similarly, we have a molecular graph where each node represents an atom and the edges represent the chemical bond. And also we have a logic circuit graph, which are connections among logic gates. So graphs can actually model complex domain knowledge. And graph embedding is an approach to extract structural information from the graph. More specifically, a typical graph embedding takes a graph topology with node attribute as input and output low-dimensional node embeddings. The goal is to preserve node similarities in the embedding space. As shown in this example, that similar nodes are in the same color, and after graph embedding, each node is encoded into a two-dimensional vector such that the embedding vectors of similar nodes are close to each other in the embedding space. And let's focus on a node classification task where the blue color represents one class and the green color represents the other. A good embedding would be we embed all the blue nodes as 1 and all the green nodes as 0. So in this case, we can achieve 100% classification accuracy. And if we consider the embedding vectors of the graph as the graph signal, and then we can perform graph Fourier transform to transform the node embeddings in the graph spectrum. Well, we can see that low-frequency components dominate the graph spectrum. On the other hand, if we have a bad embedding, as shown in this case, well, we only achieve 50% classification accuracy, which is just like a random guess in this case. And after performing graph Fourier transform, we can see that the high-frequency components significantly increases and degrade the embedding quality. So which means that an effective embedding model should behave as a low-pass graph filter. But graph filter has a trade-off between the embedding quality and scalability. Let's look at the existing model like GCN. Here is the GCN layer, and the A-tilde represents the normalized adjacency matrix with self-loop, which can be viewed as a first-order low-pass filter in graph spectrum. And recently, Lee proposed the improved GCN, which just basically replaced the A-tilde with the T's power of A-tilde. And it can be viewed as a more powerful low-pass filter to more effectively fit out the high-frequency noise to improve the embedding quality. But at the same time, it degrades the scalability due to the extra overhead. So in general, if we leverage a more powerful graph filter, we can improve embedding quality, but at the same time, we degrade the scalability due to the extra overhead. So can we improve both embedding quality and scalability at the same time? So here we propose GraphZoom, which is a multi-level framework for high-quality and scalable graph embedding. And here is the overview figure of GraphZoom. So first, we applied graph fusion to fuse the node attributes into the graph structure. And then we progressively perform spectrum coarsening to reduce the graph size while preserving key spectrum pockets. And finally, once we obtain the smallest graph, we use the graph embedding models to obtain the initial node embeddings. And finally, we use the refinement algorithms to refine the node embeddings back to the original graph. The reason why it's high quality is because with our spectrum coarsening and the embedding refinement kernels can filter out the high-frequency noise via low-pass graph filter. And our graph fusion kernel can fully utilize node attribute information. The reason why it's scalable is because we only perform the graph embedding, which is the most computer-intensive kernel on the smallest graph. So compared to directly apply graph embedding on the original graph, we can achieve runtime speedup. So let's look at closely to each kernels of GraphZoom. Graph Fusion exploits the node attributes for boosting the embedding quality. The motivation is that some models like Depot and NodeVec, they fail to incorporate the node attribute information. And so our idea is that we can construct another graph to encapsulate the attribute similarities. As shown in this example, that's given the original graph topology and the node attributes, we can fuse them together into a single fused graph, where the weight on each edge represents the node attribute similarities. So in this case, we can encode both topology and attribute information into a single graph. And our next step is apply spectrum coarsening to reduce the graph size while preserving the key spectrum properties. The overall flow of spectrum coarsening, as shown here, once we obtain the fused graph, we cluster the nodes with high spectral similarities, and then we aggregate the nodes in the same cluster to obtain the coarsened graph. The key challenge here is how do we properly cluster spectrally similar nodes. An intuitive way is we can perform global spectral embedding with smooth Laplacian eigenvectors. So graph Laplacian, L is defined as the node degree matrix D minus the adjacency matrix A. And its eigenvalues has the property that the smaller eigenvalues represent its corresponding eigenvectors are smoothed over the graph. And Schumann has already proposed that smooth Laplacian eigenvectors can actually capture the global structural properties. So we can use these smooth Laplacian eigenvectors to perform the global spectral embedding to encode each node into a low-dimensional vector, such that the node with high spectral similarities, their spectral embeddings are close to each other in the spectral embedding space. But the key challenge here is that Laplacian eigenvectors are very expensive to compute. So our workaround is we use the smooth vectors to perform local spectral embeddings. Specifically, we first generate random vectors and smooth these random vectors via a few jet relaxations. And we use these smooth vectors to approximate the Laplacian eigenvectors. So in this case, we can avoid computing eigenvectors and achieve the linear time complexity. As shown in this example, after performing local spectral embedding, we cluster the node with high spectral similarities in the embedding space, and finally we merge them together to obtain the coarsened graph. And we can iteratively coarsen graph in this way, and to obtain a series of coarsened graphs until we achieve the smallest graph size that we want. Once we obtain the smallest graph, we perform any existing graph embedding models, and then we can obtain the node embeddings on the smallest graph. And our next last step is we use the refinement kernel. We iteratively map embeddings from the coarsened graph to final graph. And by using the mapping operator M, where the mapping operator M was obtained during the spectrum coarsening. But the problem is that in this case, the node embeddings X finder may not be smooth over the graph, which may degrade the embedding quality. So instead, our idea is we use the Tikhonov regularization to further smooth the mapped embeddings by minimizing the following objective function, where the first term is the least square fitting to fit the mapped embeddings, while the second term is the Laplacian quadratic form to smooth the embeddings. To directly obtain the optimal optimizer of the objective function requires matrix inversion, which is very expensive to compute. So instead, we approximate the solution in this by using the I minus L to the power of 2, where I is the identity matrix and L is the normalized Laplacian matrix. And it can be proved that this term is a low-pass filter, so which means that the approximate solution can be viewed as we apply a low-pass filter to smooth the mapped embeddings X finder. As shown in this example, after the low-pass filter smoothing, the node embeddings are smooth over the graph, which means that we can achieve a high-quality node embeddings. Here is our experimental setup. We choose the DJI and deploy as baselines, and accuracy and macro FR score as performance metrics for node classification, and AUC for link prediction task. And our hardware setup is we use 2.4 gigahertz CPU and 384 gigabytes memory. So here are the results on smaller graph. So which can we perform the GraphZoom on both node classification task and the link prediction task by choosing DJI and DeepRock respective as basic model respectively, and it can be shown that GraphZoom achieves both embedding quality and the scalability improvement of different basic models on various tasks. And if we analyze the runtime of each kernel, we can see that the embedding time, which is the green bar in the figure, dominates the total runtime of GraphZoom. And the fusion, coarsening, refinement kernels are very efficient compared to the embedding time. And GraphZoom can significantly reduce the embedding time when increasing the reduction ratio. And this is why GraphZoom can achieve a very impressive speed up compared to the original graph embedding. Here are the results on the large graphs. We perform node classification on Fresco dataset, which consists of around 8 million nodes and 400 million edges. And it can be shown in the figure that GraphZoom achieves even better microreference score, even when the graph size is 165x smaller. And more importantly, we can achieve the runtime speed up is linear to the reduction ratio of graph size. And so basically we can control the speed up by controlling the graph size. And here is, we further analyze the performance of each kernels of GraphZoom. And the red dashed line is the DeepRock, applied DeepRock on the original graph. And the yellow curve represents we only use the coarsening kernels. And it shows that when we increasing the reduction ratio, the accuracy may drop. This is because we lose too much information. But if we apply the embedding refinement kernels, we can immediately boost the accuracy via low-pass filtering. And finally, if we add a graph fusion kernel, we can further improve accuracy by incorporating the node attribute information. And the blue curve is actually our GraphZoom framework. So here are the takeaway messages. And the GraphZoom improves both embedding quality and scalability of the unsupervised SOTA models. And the high quality is due to low-pass filtering. And also we incorporate the node attribute into the graph structure. And scalability is because we use the spectrum preserving coarsening and only apply the graph embedding on the smallest graph. GraphZoom is also a multi-level framework and is agnostic to the underlying models. And you can plug in any existing unsupervised models. Our future directions are either support supervised learning or make it work on the directed graphs. And then our code is open source at GitHub, and thanks for your attention.